Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture 27. Now in the previous lecture, we were discussing about the simplified potential energy surfaces of a ground state and excited electronic states of a diatomic molecule. And I had given you this example. This is a typical example of how the excited electronic state is going to look like and the ground electronic state is going to look like when we plot the potential energy surface, the potential energy of the system, as a function of R. And noting that this point is clearly not the origin. Okay, right? So, having said that, having seen this, we understood that in the excited electronic state, the equilibrium geometry is not the same as the equilibrium geometry in the ground electronic state. That is because, as you excite the molecule, the electron nuclear attraction is typically reduced. And due to that fact, most often you will be seeing that the R dash naught, where the dash denotes the electronic state, right, is greater than R naught. That is, the equilibrium geometry in the excited electronic state is greater than that of the equilibrium geometry for the ground state. Okay, the equilibrium bond length, that is going to be larger in the excited electronic state. Okay, and I also told you that I had stopped the last lecture by telling you that immediately after excitation, the vibrational state that we reach in the electronic excited state is not going to be the ground excited. It's not going to be the ground vibrational state. It is rather some state, much higher energy, higher vibrational energy state. Now we need to understand why this happens. Okay. Now please note the point that this transition from like nu naught in the ground electronic state to nu n dash in the excited electronic state where n is much greater than 0, that happens immediately. Okay, right? So when immediately after the transition, right, you don't go to the ground vibrational state. What is the reason, right? What can you think about it? Well, the reason, the hint, for this question is the use of the phrase immediately. We understand, okay, right? We first of all understand that there is a shift in the equilibrium geometry. Okay, that means that the internuclear distance has changed. Okay, now the internuclear distance is changed, but then when we consider the immediate transition, right, the immediate aftermath of electronic excitation is going to be the idea that the nuclei, right, not given enough time to adjust their geometry. Okay, when I say geometry, I'm talking about the distance because it's only a diatomic molecule, so distance is the only parameter that we care about. Okay, right? Not given enough time to adjust their geometry to reach the minimum in the excited state. Now, what do I mean by that? So, as soon as you excite the system, right? Now, because the ground vibrational state in the excited state geometry, right, the internuclear distance corresponding to this is greater than the equilibrium bond length for the ground state itself. The nuclei take some time. The electrons may be getting excited, but the nuclei take some time to relax to this geometry. Why does this happen? Why is it that the electrons alone move faster than the nuclei? That is because the nuclei right, are way heavier than the electrons. The mass of a proton to that of an electron is approximately 1837. I'll leave it to you as a homework to get this number. Okay, right? We're talking about something like 10 to the power 27 or 28 divided, 10 to the power minus, 27 or 28 divided by 10 to the power minus 30 or 31, something like that. Okay, right? So the ratio is going to be roughly of the order of 2000. Okay, so this being the case, the nuclei take much more time to adjust to get to a new equilibrium in the excited state. However, okay, right? However, please note that the electrons can easily get excited. Okay, as a result, you almost always, you invariably, okay, right? You invariably do not reach the ground vibrational state. You end up to another more excited vibrational state, and that is why your n, okay, right, is much greater than 0 in the mu n dash. So the answer to this question is that typically the nuclei take much more time to adjust to reach the equilibrium state, which corresponds to the mu dash naught. Okay, and that is why immediately, in any electronic excitation, because electronic excitation is always accompanied by changes in the vibrational state as well as the rotational state, right? You do not go to the ground vibrational state in the excited electronic state. All right. So therefore, this energy, okay, right? This energy transition, I'll just put it as like that for the transition. Mu naught to mu n dash, where n is something much greater than 0. Okay, right? The energy difference, okay, right? The delta E, right, is what is called as a vertical dissociation energy, right? And why is it called as a vertical dissociation energy? Because immediately, there is not much of a change in the geometry. Okay, right? The R doesn't change much. All right. So therefore, the geometry, right? The geometry of the excited state and the ground state, they more or less remain the same. Nonetheless, when I say the geometry remains the same, the internuclear distance remains the same. Okay, right? But the electrons have gotten excited. Are we clear? The electrons have gotten excited. Okay. The electronic movement is much more, but then the nuclear movement is much less. Okay, right? So this distance is what is called as virtual dissociation energy. Now, what happens, I recall that all along in our discussion for the transition from mu naught to mu n dash, okay, right? We have been using the phrase immediately. The key phrase here is what happens immediately after, the electron, the molecule gets excited. All right. But, I haven't defined a time scale yet. Okay. I haven't defined how immediately is immediately. Okay. Don't worry about it. But subsequently, okay, once you have a molecule in a higher vibration state, right, nothing can stay in an excited state for a prolonged period of time, right? So what happens is that eventually it has to trickle down to a lowest energy state, right? So that can happen, that can happen by like the energy getting emitted, the excess vibrational energy getting emitted, and eventually, right, the geometry will change, right? And after some time, right, your transition from mu n dash to mu naught dash, okay, right? We're talking about in the excited electronic state, right, the transition happening from a higher vibrational energy state to a lower vibrational energy state, okay, right? So mu n dash has to happen, will happen as the excess vibrational energy is emitted, and this delta E, okay, right, the delta E and the difference between the ground vibrational state, okay, of the ground electronic state to the ground vibrational state of the excited electronic state, right? Now let's just call it as delta E2, right? That is actually called as your adiabatic dissociation energy. So these are two useful measures. Okay, so these are two useful measures, right? That you can experimentally measure. Okay, depends on your experimental sophistication. You can measure the adiabatic dissociation energy as well as the vertical dissociation energy, right? To understand, okay, right? To understand how the molecular changes have happened between the ground state and the excited state, the ground electronic state and the excited electronic state. Okay, and not just this. See, beyond the introduction of these two concepts, the vertical and adiabatic dissociation states, you get much more information from these two curves. And recall, why are we having all of this discussion? It is in the context of astrochemistry, right? It is in the context of astrochemistry and to see how molecules were detected in space. So this should be page number 4 and see. So, okay, now let's say that, like you excite a molecule, it goes to a higher vibration state in an excited electronic state, and the molecule goes back to the lowest vibration state in the excited state. Now, of course, again, the molecule cannot stay here forever, right? Through various phenomena, okay, right? By various several phenomena. I'm not going to go to the details immediately, okay, right now. What happens is that eventually, right? Eventually, the molecule will come back from the excited state to the ground state, okay, right? The molecule will come back from the excited state to the ground state, okay, right? And in this process, note this beautiful process, okay? Note, in this process, okay, right? As molecule emits energy to return from the electronic excited state to GS, what can happen is that some rotational energy states some higher rotational energy states, okay, can also get occupied. Recall that this is a very, very important point, okay, especially in the context of astrochemistry, and I will tell you why soon, okay. So what am I telling you? Well, so far our discussion was only based on the electronic state and the ground state, okay, the electronic state and the ground state, and we included only the excited state and the ground state, considering electronic states, okay. And we saw that, okay, the vibrational states can also change, okay, right? Initially it is not going to be the ground vibrational state, and eventually the molecule will come to the ground vibrational state, okay. We never even discussed anything about the rotational energy states. Now what happens is that if you supply, you give the molecule some energy, now the molecule, is like emitting the excess energy to come back to the ground state, and as it comes back, right, recall that between U1 and U0, if you go back to the previous lecture, I had shown you that between U0 and U1, there are also rotational energy states, right? So the molecule will also be populated, not just in the ground state rotational energy, but some higher rotational energy states will also be populated. And if the energy gap between the two rotational states isn't high, okay, right, you can see that in the electronic spectrum itself, right, you can see some lines corresponding to the rotations of molecules happening between any two rotational levels also. So in the electronic spectrum, okay, in other words, why do we speak about all of this here? We see that the message is that for astrochemistry, I'll tell you why it's relevant for astrochemistry soon, right? From electronic spectra, you can get critical info about molecular vibrations and rotations too. Okay. because the electronic transition is associated with vibrations and rotations, right? It is very important to note that you can get critical information about vibrations, rotations too. Now, in the context of astrochemistry, this information, right, proved to be crucial. This information proved to be crucial and critical, okay, in determining two facts. So way back, okay, right, way back in approximately 1935 to 1942, okay, in that period, okay, right, a lot of work, notably by Canadian astronomers, okay, and one person by the name, I might be spelling his name wrongly, if I'm correct, it's notably by this person, okay, McCarroll, who was an outstanding astronomer, okay, and a spectroscopist, right? So along with some others, including the Nobel laureate Gerhard Herzberg, okay, right? Now, this person, right, observed, okay, right, as always, you want to observe some spectral lines coming from a star, okay, right? So observed spectrum of light coming from a star. If I'm correct, the star's name is something like, I don't know how to pronounce it, it's OP, also spell it, okay. This is what it is. I don't know how to pronounce it, but this is the OPIUICHI is the correct spelling, if I recall. Maybe I'll check the spelling and get back to you in the next class, and also the pronunciation, okay, yeah. So they observed spectrum coming from a star, okay. And what spectrum? They're talking about electronic spectrum. This is critical, okay, right? So they observed like electronic spectrum of light, coming from the star, okay, whose name starts with an O, all right? So what they noticed was that, the lines, okay, from the electronic spectrum, right, from the electronic spectrum matched with electronic spectra of CH radical, CH plus, and CN radical. Now, what are the structures of these three molecules? This will be page 7 now. CH, well, and then 1, 2, 3, 4, 5, 6. This is going to be CH, okay, right? I mean, hydrogen's valency has to be 1. So all the other, electrons of carbon are going to be, not going to be part of the chemical bond formation. Okay, this is CH. And then you have CH plus. All right, you take away one electron. And so it has to be coming from the carbon. Okay, this is CH plus. And the next species is CN radical. Right? Conventionally, the lone pair is on carbon. Okay. So notice this point. So these three structures were obtained. Recall in our earlier class about the various species and the molecules which were obtained in space, which were detected in space. I gave you the examples of these molecules, and we also saw that carbon need not be always in its tetravalent state, correct? Unlike what is predominantly seen on Earth. Some intermediates can also be obtained in space. Okay, so consistent with that, they obtained the spectra of these molecules which were known from Earth. Okay, on Earth, as part of some reactive intermediates, they could obtain the spectra of these molecules, and they matched exactly, the electronic spectra matched exactly with it, with those obtained from the starlight. What is the conclusion? The conclusion is that the interstellar medium, that is, the interstellar medium, therefore, contains these molecules. So these were the first molecules. These were the first molecules to be detected in space. The story doesn't end here, though. Okay, there is some very interesting aspect associated with these molecules. I'll come back to it. But before that, please note they were obtained as part of electronic spectra. Okay, electronic spectra, and this particular transition corresponding to CN was approximately around 3,900 to 4,000 4,000 wave numbers, I think. I'll check for the exact number in the next class. So based on these transitions, okay, right, they actually obtain the species. Are we clear? Okay, they noticed that these molecules could be detected in space. Now in our course, in our astrochemistry course, again recall that this is the first time we're actually talking about the detection of molecules in space. When we understood that the sun was made up of elements present on Earth itself, we were only talking about single atoms, right? Atoms such as like potassium, calcium. We never talked about multiple atoms coming and forging a molecule, right? And the detection of molecules were never discussed. We stopped with atoms and then we took a detour. We took a detour to understand various aspects of molecular motion and electronic transitions. And having understood them, we're now coming back to say that using electronic spectrum, right, which involves the transition from a ground electronic state to an excited electronic state, people, especially Becquerel, right, who was an outstanding astronomer and spectroscopist, they detected these three molecules from 1930s to 1940s. Okay, right? Are we clear with this? Okay. There is one more interesting aspect. Now, going back to page 5, right? What did I tell you? From astrochemistry, the relevance for astrochemistry, from electronic spectra is that you not only get information about the electronic states involved, okay? You also get critical information about vibrational and rotational states also, especially because, as a molecule gets excited and as it comes down, if the rotational energy levels in the ground electronic state, if they are not too high, okay, if they are like very little only, in that case, there could be a population. There could be a population of the molecules not always coming back to the ground rotational state of the ground electronic state. It could also be some excited state also. Okay. Now this message was absolutely critical in determining a key parameter of space. I'll tell you what it is very soon. Okay. So we now know that these molecules have been identified in space. Okay, right? That's the good news. So finally, we've come a long way in this course, starting from understanding the different conditions to seeing how molecules can actually be detected in space being on Earth. Okay, isn't that very cool? Right? Yeah. Let's now consider this particular molecule. Okay. Now this person, again, Andrew McCarroll, I'm just going to say it as AM. Okay. He noted that in 1941, I will give you the exact reference, sometime soon. Okay, approximately around 1941. That okay. Now, in the electronic spectrum of CN, right, the rotational states, the first excited rotational state in the ground electronic state. You understand what I'm talking about, right? We're talking about the ground electronic state. We spend a lot of time to describe that a ground electronic state could have vibrational states, and between any two vibrational states, we could have rotational states. Okay. So in the electronic spectrum of CN, right, it was noted that the first excited rotational state in the ground electronic state was also occupied. It was not just the ground electronic state, okay, right? And you could have the, how do you get to know they're occupied? This is by comparing the spectral signals corresponding to the R0 to R1 transition, okay, right? Are we clear? I have not told you so many more details about the individual spectra, which we shall soon see in subsequent lectures. But for now, you get the idea that from the electronic spectrum, because you can get also information about molecular vibrations and rotations also, McCarroll in 1941 got the critical information that, some molecules of CN are not always in the ground rotational state of the ground electronic state, but some of them could also be in the first excited rotational state. All right. How did he do this? He could do this by measuring the intensities. Okay. So how did he get this information? He saw that the ratio of the rotational lines. I mean, the lines, the spectral lines so the ratio of the spectral lines corresponding to a transition from R0 to R1. All right. So, you can get the ratio of the spectral lines corresponding to a transition from R0 to R1. This can be experimentally obtained. Okay, right? Now, based on this, okay, right, you'll be getting two lines. So, the intensity of the two lines, okay, I2 to I1 is proportional. Okay, don't worry about the equation. I'm not telling you where I'm getting this equation from. Okay, right? That is proportional to approximately, and this information. So this is experimentally obtained, right? This information can also be experimentally obtained. I haven't told you how yet, okay, right? Haven't told how. How experimentally obtained. But please understand that, okay, right? You can always have intensity of, as the molecule comes back from an excited electronic state to its ground state, okay, not just the ground level is populated, but the ground rotational state is populated, but the first excited rotational state of the ground electronic state is also populated. Okay, right? As a consequence, when you measure the electronic signals, I'll put it this way: I1 to I0. Okay, you get signals from both the ground state as well as the first excited state. Now, this was found to be proportional to this particular factor. Okay, e to the power minus delta E by kb over t, where kb is the Boltzmann constant. All right, which is R by Na. I haven't told you how this is obtained. Okay, we shall see this, when we discuss more in more detail about rotational spectroscopy. I haven't also told you how this delta is obtained, right? Although this can be obtained by experiments. What experiments I haven't told you. Okay, this is also obtained from experiments. By looking at the spectrum, you can get this. So based on this, okay, right? Based on this expression, this is experimentally obtained. This is experimentally obtained. This term kb, we know it's a constant. Based on this, he could measure T. Okay, I'm just calling this expression AM in honor of Andrew Mackerel. Okay, right? Based on this information, okay, based on this information and some constants, okay, involving the degeneracies, etc., etc. AM, okay, based on equation AM, right, we can get the temperature, okay, right, the temperature of, more specifically speaking, I should call it rotational temperature, right, but I don't want to confuse you by using too many jargon at this stage, so I'll just use the word temperature, okay, loosely, right, temperature of the gas in ISM. We're talking, when I say gas, I'm talking about the CN radical, okay, and that was measured to be approximately 2.7 Kelvin. When was this? This was in 1941, okay, right? Now, recall that, when in our discussion of the dense molecular clouds, the diffuse molecular clouds, etc., we keep talking about, the places where molecules are found in the ISM, the molecular clouds, the temperatures are very cold. That is a feature we've always been constantly discussing in this class, right? Now, here was an experimental determination, starting from the spectrum. I haven't told you many details yet, but it is well established. It is very well established that, starting from experimental spectra and starting from and some theory, okay, and some theory involving quantum mechanics, that also I haven't told you, okay, using electronic spectrum, right, based on the difference between the population in the ground rotational state and excited rotational state, okay, right, it was determined that the ISM is actually a very cold place. All right, are we clear? So the temperature in the ISM, in some region of the ISM, was actually determined as early as in 1941 using spectroscopic principles. On that note, we shall continue this lecture in our next class. Thank you.